Here we are with your week 2 video for NUC 110 Nuclear Reactor Systems. For this week, you'll find your assignment under Courseworks on Blackboard, so I want you to review the PowerPoints under test number 1. That's going to be BWR, Reactor Vessel Internals, and PWR Systems. We'll do those now. And then I want you to complete quiz number 2. So basically, it might be a good idea to do this 3 or 4 times. It's something that you'll be asked to do at GE, is to label all the different components here. So you can see the arrows. You can label more than the number of arrows if there's something else that you know or some other way that you found it in the slides. So just label as many things on here as you can and try it a few times, and then just take a picture and email it to me. So let's take a look at the 2 PowerPoints for this week. So hey, look, it's the same picture. So we're going to go through all these different pieces and parts, where they are and what they do. So take a look at these reviews, just focusing on the quiz and things like that. And you can see most of it is what was on the quiz. Then there's a few slides of objectives. So what's the purpose of the reactor vessel? So we want the flow of coolant delivered to the vessel to be distributed correctly. So all the different parts of the reactor need the right amount of water. We want to locate and support the fuel assemblies. So put them in the right place and make sure that they are not going to fall. And then the most important one is to provide an inner volume containing the core that can be flooded during a LOCA. And LOCA is loss of coolant accident. So if we start losing water, we want to be able to make sure that we can flood this thing back up. And we also have to be able to refuel. So every 2 years, we have to be able to take this thing apart and put it back together. So the reactor vessel assembly is going to give us a volume in the core that can be submerged in water for moderation, cooling, and power generation. So the vessel's job is very, very important. Serves as the high integrity barrier against leakage of radioactive materials to the dry well. So if something happens to a fuel bundle and it starts to leak, I want to make sure that it cannot leak out of the reactor and into the dry well, and potentially out of the dry well and into the building, and out of the building and into the people. So I have defense in depth there. And it's also given us that floodable volume that can be cooled in the event of a breach in the reactor systems, and it's inside the dry well. So here's what it looks like. This is an old picture from the 70s, and it's turned on its side, of course. You can see there's a lot of different penetrations here for different water coming and going, different sprays coming and going, and the fuel is actually in this range here where you see there aren't any penetrations. This one is close, but this area is where the fuel would be. So 70 feet tall and about 18 feet in diameter. And there it is on a barge bringing it in. So they put it on 2 little tank treads here to actually get it over to the dry well, which you can see here. So this is the dry well before there was a building. So they're going to sit the reactor in there, bolt the head onto the reactor, bolt the head onto the dry well, and then they're going to build a whole building around this. So you can see them actually lifting it up and getting ready to drop it into the dry well. And then there it is with the head in place. So this is the top of the reactor, and it's sitting inside the dry well now. There's 64 bolts that are going around here that are very, very heavily tensioned to hold everything together. So it's part of the building, right? You just saw that they put the reactor and the dry well in there before they actually built the building. And that dry well is giving us a biological shield as well. So all the concrete here that you can see is going to slow the radiation down so that it can't as easily get from the reactor to us humans. So there they are standing on top of it. Oh, this is down before they sit it in there, right? So they're getting ready. This is the ring, the pedestal that they're going to sit it on. And then here's a little cartoon mock-up. So this is the reactor, and you can see these biological shields here in purplish pink, and then the dry well going all the way around, which is more biological shield, more concrete. So that biological shield is a couple feet thick, and it surrounds the whole vessel, and it's supported by the pedestal as well. And it's just, if you're in the dry well, that biological shield is going to protect you. And it also is going to keep the neutrons in. So neutrons are one of the tougher types of radiation, and they can cause a lot of problems. So we want to make sure they don't get to our dry well components. So radiation is bad for humans. It's also bad for machines. If you looked at Fukushima at all, some of the robots that they sent into Fukushima died from radiation. So we're going to put insulation all around the reactor as well to keep that heat in. So that's something that you're going to be taking off whenever you go to refuel the reactor. So here we go. Now this is where it starts to get a little bit more complicated. So the core shroud, and basically we want that floodable volume. So when we look at that reactor, you would think that it's a floodable volume, but it does have holes in it, right? So some of those holes were near the bottom and some of them were near the top. You can actually see one of the holes right here near the bottom. So imagine a steel beam falls off and chops this pipe off. Well, that's going to drain all the water out of here. So I need to do something to prevent that from happening. And what I've basically done is put another pool inside here. So out here, you can see a little tiny jet pump is what this one's called. And inside that jet pump, there is basically like a kiddie pool. Imagine that you have a nice big swimming pool and you're worried about it springing a leak. So you put a kiddie pool in there and, make the kiddie pool out of steel, but still, this area is not connected to these holes that are lower down. There's a few different ones here. So if this pipe falls off, the water on the outside is going to run out, but this core region is still going to be able to be flooded. So even if you poke a hole in the bottom of the reactor, you're still going to have this kind of kiddie pool in there that you can fill up. And I'm using kiddie pool very, very loosely here. So there's a few different names for this. So the core shroud has given us that floodable volume, right? This blue is the core shroud. So outside of there is called the downcomer region or the annulus region. So water that's coming from up higher can go into this region and then it'll get pumped down and around and into the reactor, into the core, let's say, because this whole thing is the reactor vessel. So the core plate is what all these different is what's basically going to keep all the holes and keep everything aligned. So all the fuel bundles, all the control rods, and things like that are going to be going through this core plate. This is what it looks like from the top. These little X's are going to be our control rods, and then all these holes are going to be filled up with fuel. So if you were looking down from the top, you could grab this fuel bundle with a crane, or sorry, grab this control rod with a crane and pull it out. And eventually the fuel bundles are also going to be in some of these channels. There it is looking from up high. So that's going to be the bottom, and where he's standing is going to be up at the top, right? These are 2 feet. So just to give you some reference points. So that top guide was what he was standing on. It's a matrix just to hold the fuel assemblies and basically make sure they can't fall over, right? Lateral support for the top of them. There he is. So he was just standing on this. Now we're standing on the bottom and looking up. So now we are dealing specifically with BWR, reactor vessel internals here. So some of the components on the top need to get the steam out because I cannot give wet steam to my turbine, which that seems wet steam. What does that even mean? So that steam that's going to the turbine, we want to be very, very low in moisture content. So you can imagine if you hold your hand over a boiling pot, 6 feet over it, please, eventually some moisture is going to build up on your hand. And what we don't want is for that moisture to build up on the turbine because it can hit the turbine with enough force to actually cause damage to it. So what we're going to do is basically make the steam take a treacherous path as it's leaving the reactor. So it's going to have to make some switchbacks and some squiggles and turn back and forth a few times. And the purpose for that is to get as much water out as possible. So these steam separators and the next one is steam dryer, they don't have moving parts. They're just creating some cyclonic action. So make that steam do some work going back and forth. And any water that comes out of that steam, because it's moving back and forth, is going to go back to that downcomer region, which is why it's called the downcomer. So the water dripping from these steam separators basically goes into some gutters and goes back down to that downcomer to get pumped back through the reactor again. So that's the steam separator inside there. It's just lots of pipes, and they have that treacherous path. And you can see the internals here. Basically, there's like a nozzle here, and all that nozzle's doing is importing some turbulent flow on our steam. So as it gets slung around, some of that water is going to fall out just because it has the wrong momentum now. So if the steam was able to carry it straight, it probably would be able to carry it straight. But since it's going through this treacherous path, it's going to drip back down and go back down to the downcomer. So there's the steam separator again. You can imagine on the steam going through all those different pipes and tubes there. And then above the steam separator is the steam dryer. So we started with some fairly wet steam up here. So the quality was 10%, which means 10% steam and 90% water. So now when we get here, we're at 0.25% moisture, right? Water. So the steam is obviously still made of water. So that's why we can't get this to zero, right? We can't get all the way to 100%, but we've got as much of the moisture and humidity out of it as we can. So we got that steam quality all the way up to 99.75%. So it's 99.75%, steam and 0.25% liquid water. So that way, the turbine doesn't have to deal with getting hit with all those waters. Um, so the steam dryer, it's the same thing, the same sort of look as the steam separator. So if you were to able to look inside, we're just creating a treacherous path. So you can see basically just all these different baffles are going to make it go through there, make it dance a good dance. And as it does that, the water will hit the edges and drip back down into that downcomer. So there you go. There is our treacherous path as it goes through these moisture collection hooks. So now let's look at another major component in there, the jet pumps. Again, no moving parts. So you're going to quickly notice that the reactor vessel does not have very many moving parts in it. The fuel does not move, the jet pumps don't move, the steam separator and steam dryers don't move because moving parts are more prone to breakage, and when something breaks, it might end up in the fuel. So we want to make sure that that does not happen. So these jet pump assemblies basically are giving us a continuous internal recirculation path, and it's force and flow through the core. And if for some reason we lose our pumps, it'll still let natural circulation occur, which natural circulation just means the hot is going to rise up. And when that rises up, cold will come in underneath. And as it heats up, it rises up and just make that natural recirculation. Here is a jet pump. So we have the water coming in the middle here, and then left and right is going to be two different jet pumps. And over here's another one. The water comes in the middle, it goes up, and it's going to go down these two different jet pumps. So there's altogether 20 jet pumps inside the reactor there, and they're all in that downcomer region. Up at the top of our picture, right, this is where we said the water was coming in. We get this little thing called a ram's head. And if you are an RST, this is something that you're going to spend a lot of time looking at because this water is coming in and it's hitting right here on this ram's head. So all day, every day, we have tons and tons of pressure going right here on this ram's head, and then it's going either left, it's going both left and right, and it's making another turn here. So all that water all day is basically corroding these different edges and potentially causing problems. So recirculation flow. I have two pumps outside the reactor vessel, right? I have two recirculation pumps, and they are going to take water from the downcomer. It's going to go through this and into my jet pump. And as it comes into the jet pump, there's an opening here and a nozzle. So that nozzle is going to create a low pressure point somewhere inside um, this piece, right? Called an adductor, right? Venturi effect is the fancy word, but basically this blue line comes down to form a nozzle, and at the tip of that nozzle is a low pressure, and then that nozzle is inside this little piece of pipe, but it's actually exposed to the downcomer. So the water from here is going to rush in as well. So I have water getting pumped through with something with moving parts outside the reactor vessel, right? And it's going in this outlet line into the downcomer and getting pushed in, and then eventually underneath the vessel and into the reactor core, right, where the fuel is. So you can just imagine the inside of this thing. This is an open pipe. This gray part is open, right? The blue piece is sticking down into the gray part, and the end of this blue piece is just a nozzle. And that nozzle makes a low pressure, and nature does not like low pressures, and pulls in the water from the different parts and takes it through and up into the reactor core. So if the jet pump falls off, it's not going to be a big problem. So this is a much bigger picture, much better picture of our kiddie pool. So say, here we go. This suction line just broke. It fell off. So all the water from here is going to start to drain. Sound caught me off guard there. So So the water is going to start to drain down, and you can see this is as low as it can drain because now we are to the kiddie pool. And some of that fuel is uncovered now, but I have another system up here that can help me make up. So even if this breaks, you can see the water level here is drained all the way down. Um, and that's a huge issue out here still, but at least inside here in our other pool, our pool within a pool, we still have some of this fuel covered, and then I can start spraying water on top to cover this last third. So another component, the control rod. There's 137 at Brunswick, and what they do is eat neutrons. That's their whole job. So uranium 235, in order for it to split and for us to make energy, um, we need to have a neutron come in and hit it. So in order for me to have brakes, I need to have something else that also absorbs neutrons, but that does not cause a reaction like a fission. So that's what my control rods are going to do, and they are controlled by the control rod drive system. So there's also down here on the bottom, just in case my control rod falls off, it's basically like a little parachute so that it'll fall a little bit slower and give the control room a chance to figure out what's going on while this thing takes a few extra seconds to fall down because of this velocity limiter down on the bottom. You can see right there it is. It's kind of making like a little metal parachute. Thing's still going to fall out pretty fast, but at the very least it'll slow it down a little bit. You can see this thing is 12 feet in length, and a fuel bundle would basically go in each crevice. So this thing is making kind of an X or a cross, and there's going to be 4 fuel bundles around each one of these control rod blades. And there you go. You can see the control rod. Here's the handle that we could use to change it out. And then there's going to be 1, 2, 3, 4 fuel bundles around it. And that's going to be its primary job, is controlling the power that's coming out of those 4 fuel bundles. So some more pieces and parts. So we just talked about that 2/3 of core is going to be covered just by our pool. And we're going to have the last third sprayed in by core spray. And a sparger is just one of those things that basically diverts the water. So we don't want the water to blast straight down into the reactor. We want it to blast all over the place. So if you've ever seen a fire main go off inside of a building, that thing that's on the top is a sparger that causes the water to go all over the place instead of just straight down. There's 2 different core spray systems, and each one has its own sparger to basically divert that water and make sure that it covers the whole reactor. And if either one of these spargers breaks or the core spray system breaks, we can still completely cover the fuel with only 1 core spray system, even though we have 2. And that's what they look like. So this is both spargers, top and bottom, and you can see they go all the way around 360 degrees. And when it hits this, it's just basically going to spread out. And I think right here you go. You can see it's getting nice, good coverage of everything in the reactor. So feed water spargers are doing the same thing. So all the time I have feed water coming into the reactor, and it's going to evenly distribute that feed water so that it doesn't, again, just blast a hole. We don't want to erode the side of our reactor vessel just by blasting this feed water into it. So that sparger is going to, the water that's coming in all the time is called feed water, and it basically gives it a nice even spread. So that's what their sparger looks like. The same basic idea, we're just a little bit more zoomed out here. So here we are, the big picture. So you got the steam dryer and the steam separator or moisture separator up here on the top. And you can see the water level is up close to these moisture separators, but it needs to be below them. Otherwise, they aren't going to work at all. Here's our feed water. There's 4 of those coming in, and that feed water is going to come in and feed my reactor because it needs to be covered in water all the time. Over here's that jet pump nozzle. So the part where I'm getting that low pressure, and then you can see now that this is all covered in water. So as this water comes to the tip of that nozzle and gets that low pressure, it's actually going to pull this water, all of it. Well, eventually all of it is going to get pulled into these jet pumps and then come underneath the reactor. So here we have the control rod drive housing, and then attached to the control rod. The top guide is here, and the bottom guide is here, or core plate. And those 2 are going to be what's actually giving structural support to the fuel. So the fuel would be in here. We don't have it pictured. There is 1 fuel bundle and one control rod here. And then here is where the recirc is getting its water from. So the water is coming out and going to that recirc system and getting pushed back into these jet pumps. So it doesn't just come in up here or something like that. It goes directly into the jet pumps. So we'll talk more about jet pumps as time rolls on here. And it looks like those are the big pieces and parts of the reactor vessel. So moisture carryover, like I said, we cannot have water get into our turbine. It's going to mess with the turbine. It's going to decrease the efficiency. It's going to wear the turbine out, and it's going to actually increase the amount of reactivity or radioactivity that is in the balance of the plant. BOP is balance of the plant, so everywhere besides the reactor. So as we move forward, you're going to see a lot of these technical specifications. So just like the tech specs on your phone, it's got 128 gigs and it's got a certain amount of RAM and this, that, and the other. Those are your tech specs. This reactor has to be inside certain technical specifications. So one of those is reactor vessel level shall be greater than the top of the fuel. So the fuel needs to be covered in water all the time. Otherwise, we have to shut the reactor down until we can actually get it covered. And then the reactor pressure shall be less than 1,325 pounds per square inch on a gauge. So if it gets higher than this, we risk blowing the reactor up, right? It's not built for these pressures. It's built for around 1,050 psi. So we've given ourselves a little bit of leeway, but we want to make sure if we go above this, the NRC is going to force us to go in and inspect every little piece and part in the reactor to make sure that there's no potential for an accident moving forward. So both of these are kind of like the law of the land. You can see this big shall in here. That's always a scary word, and it's a government word, right? The NRC had us put this word in here. So if that water goes below the fuel, we're shutting the reactor down indefinitely while we go in there and take a look at all the fuel and make sure that none of it was able to melt. And the same thing here. If we get above this pressure, we're going to shut down and make sure everything in the reactor is still working correctly. So as you go through these objectives, you'll see some definitions for all the different pieces and parts in there, and it's a great opportunity to review. So make sure you look at these objectives and review them, and then let's take a look at the PWR systems. So if you need to take a break, please pause and do so now. So you can see the first few slides are all reviews, so make sure you look over those reviews. That'll help you out a lot. And then here we go. So I've got my reactor, and then in this case, I have 4 steam generators. Each steam generator has a pump attached to it. So the hot water from the reactor goes through the steam generator, and this water is getting cooled off, while the other side of the steam generator is getting heated up and turned into steam to go off towards the turbine. So this water gets cooled off, and then it hits this pump and gets pumped back into the reactor. And off one of these loops, I'm going to have my pressurizer, and you can see that there's only so much water in there. We talked a lot about how the pressurizer works in the last week, so please go back and look at that if you're forgetting how it works, but it has heaters and sprays. So if the pressure gets too hot, or if the pressure is going low, it can heat the water up. If the pressure is too high, it can spray and condense some of that steam and lower it down a little bit to be able to keep it at that 2,250 pounds. And for this PWR, remember that this is the only steam in the whole thing is inside the pressurizer. The reactor is water solid, and we just looked at the BWR, so you can see that anywhere above the steam separator and steam dryer is going to be steam. So they work very differently. So there's many different types of PWRs. You can see this is a Westinghouse, which is just a company, and it's a 2-loop plant overview. So there's 2 steam generators, and they're just very big, right? The reactor's here in the middle. It still has a pressurizer, and it has 2 of these reactor coolant pumps. There's a Westinghouse 3-loop, a Westinghouse 4-loop. A different company, Babcock and Wilcox, has a 2-loop. Combustion Engineering has a 2-loop. So these are just different companies that have made PWRs at one point or another. So this drawing you're not as responsible for. I focus more on boiling water reactors, but you can see a lot of pieces that we've already seen, right? The lower core plate, some different nozzles, and different things that are very similar to what we saw on the last drawing. One major difference you'll notice is that the control rods are coming in from the top. So the top is just straight up better. It's safer. Gravity can push those control rods in. But if you'll remember, in our BWR, we have the steam separator and the steam dryer up there on the top. So we can't actually have the holes in those things. Otherwise, they're not going to work as intended. So in the boiling water reactor, you're going to see those control rods come in from the bottom. You can also see there's lots of notes down here for you to read. If there's something that you're not understanding, you can do that. And please feel free to ask me any questions that you may have. So the steam generator is just a type of heat exchanger, and it's taking the hot water from the reactor, and transferring that heat to the secondary loop, which is where the turbine is. So it's just a normal heat exchanger, and there's also some opportunities to spray water in there in any kind of an emergency. And it's just a relatively simple piece and part once you understand heat exchangers and how they work. So these are just a couple different cutaways of these steam generators. So a reactor coolant pump is just a pump. Here it is really broken down with all the different pieces and parts. But the big picture that I want you to know is that it's a pump, and its whole job in life is to push water from the reactor, or sorry, from the steam generator back into the reactor. So that water is going to lose some energy as it goes through the heat exchanger because it's kind of a treacherous path. And as it does that, we're going to need to push that pressure back up to get it back into the reactor. So the pressurizer, we talked a lot about that one last time. Please let me know if you have any questions. But remember, if the pressure gets low, the heaters kick on. If the pressure gets high, then these sprays kick on. And we have a tank over here just in case it gets too high. Or if I need to, I can take water from here and spray it back into my pressurizer. So here it is with the secondary loop as well. So remember that I have more than one steam generator. So here's my core, the pressurizer is attached, right? It goes through the steam generator, and that's going to cool this water down. And there's the reactor coolant pump sending it back in. So now this secondary loop, it's cooling the water off on this loop, and it's heating the water up on the secondary loop. So this water is actually going to get turned into steam here, and it's going to go over to my turbine, right? And spin this turbine, which spins my generator, which makes the electricity so we can charge our iPhones and things. And then as that steam is used up, it's going to go through a high pressure turbine and low pressure turbines. And we're going to use as much energy as we can. Once it's used up, we're going to send it into the condenser, and we're going to turn it back into water. And it says circ water here. That's my river water coming through just to cool this condenser off. And now that it's cool, I can pump it. I can clean it up some and heat it back up, pump it some more, and it's going to go back into my steam generator. So I just want to heat it up for efficiency's sake. And I'm actually going to use some of the steam from up here in different places. So I might take a little bit of low pressure turbine steam and run it through this heater to heat the water back up. I might take something straight from here, right? I might take something from here and run through this high pressure heater to heat it back up, because I don't want this too much work to have to go on here. I want the water to be really close to boiling whenever it gets to this steam generator. That way I'm going to boil more water if it's really, really close, right? If it was, we'll say 211 degrees Fahrenheit, when it gets here, it's going to be easy to boil. If it's 90 degrees Fahrenheit when it gets here, it's going to be really hard to boil. It does boil at a higher temperature in there. It boils around 550 degrees Fahrenheit. But it's the same idea, right? We want this to be coming in here as close to boiling point as possible. So another system is this chemical and volume control system, and we'll talk more about this one later. But its job is literally just to clean all the water up. So you have a volume control tank, a pure water tank, a boric acid tank. So sometimes I have too much boric acid, because remember they use boron in this type of reactor to control power. So if I have too much boric acid in here, well, I'll just dilute it. I'll put in some pure water and take some of the water that's in here out. Right? If I need to lower power a little bit, all right, let's get the boric acid going. We'll put a little bit of that in here, and that'll lower power back down. And that's just a very fine control. The other way is, of course, these control rods. So I have two different ways to control power, and one of them is this CVCS, Chemical and Volume Control System. So I also have two demineralizers over here. So, right, it's controlling the chemicals, it's controlling the volume. So it's cleaning up that water that's coming through and just making sure that I don't accidentally corrode my fuel. And we talked about last time, these demineralizers need cool water. So I'm going to go through these heat exchangers just to cool everything off before it gets to these demineralizers. And then you can see on the way back, it's going to have to go back through this heat exchanger. So that's why it's regenerative. So I'm heating the water back up before it goes into the reactor. And in the act of heating this water up, I'm actually cooling this water off that's on its way back towards the demineralizers. So they're all going to have a big containment around them. You can see there's sort of dry well built in here, and then this big containment building. And you can see there's actually a way to spray the entire containment. So this is kind of like their dry well. So the steam generators are going to be inside there, and this concrete is what's going to be protecting all the workers. You can see layers and layers of concrete around the reactor to protect the workers from radiation. So the comparison, right? We've got a whole extra loop here. So I've got the core on my primary loop, and then there's a secondary loop with the steam generator. So over here, I'm just boiling water directly from the reactor, sending it through the turbine to the condenser and back into the reactor. So over here, everything is contaminated, right? I'm taking stuff from the fuel, little bits and pieces of things can leak out of those fuel bundles over the long haul here, and everything over here becomes contaminated. So if I'm working on the turbine and they give me a choice between a boiling water reactor and a pressurized water reactor, I definitely want to work over here because this is not contaminated. It doesn't have any radioactive particles getting to it. And remember from the picture last week too, you can see the turbine can actually be sitting outside. So here are the objectives again, and you can see this is all, again, a review. It's given us all the definitions for the different terms that we went through. So please let me know if you have any questions, and I hope you have a good week.